Thank you so much for the introduction. My name is Enrique Pena-Martinez. I am a PhD candidate in electrical and computer engineering at NC State University. And let's see. Perfect. And in this presentation, I will tell you how my team and I have been scaling phenotyping research on sweet potatoes to industrial levels. I will also talk about potential solutions on translation to sub-Saharan Africa crops like cassava and breeding sweet potato programs. About 15 years ago, large sweet potato companies began adopting novel optical sorting technologies that look like this in North Carolina. And they are very complex, but very effective at sorting millions of sweet potatoes daily by shape and by size, and increasing productivity and revenues. However, when a sweet potato company decides to invest in such technology, they really want the full potential of the technology. And I can tell you right now, the full potential of these technologies is still untapped. So thankfully, the few packing companies that have adopted such technologies, which cost about $1 million, have really opened the doors for academics like us and industry to partner up and conduct or enable industry-scale phenotyping research in the United States. So SweetApps was founded in 2019 to create new technologies that reduce waste and increase value for North Carolina sweet potato farmers, growers, and packers. And what we essentially are is a group of interdisciplinary people that focus on artificial intelligence, big data management, and cloud computing. And we focus on making the whole sweet potato post-harvest more holistic, using scanners like the optical sorters, but also novel technologies in AI, data pipelines, and cloud computing. So we partnered up with these companies that have these optical sorters in place, and they have the infrastructure in place. And we obtained access to their data reports and their operations. We were out there in the field. We saw how they were picking the sweet potatoes. We saw how they were placing them in bins and then putting them in trucks and transporting that into the storage. We saw how they were looking at the bins and visually inspecting what grades they had in there. We saw then how they were washing the sweet potatoes and then conveying it, throwing them into the sorting machines, and then packing them. We quickly realized that there were some gaps, with the optical sorter, and we thought, okay, let's try to address those gaps. And this was an opportunity for us to implement our own optical sorting or optical scanning machines in the post-harvest pipeline to facilitate real-time phenotyping, but also real-time decision-making. So our idea was, let's look at the transportation stage and the conveyance stage and try to implement low-cost scanning solutions here. And the question is, can we obtain the same phenomic distributions that we're seeing with the optical sorter, the more sophisticated sorter, but earlier during the transportation and conveyance stage? For large packing operations, this would mean obtaining or being able to see what's coming in through the pipeline before actually sorting the produce. Right now, what happens is they're harvesting everything, trying to fulfill orders by their customers, and then turns out that sometimes they cannot fulfill those orders because they realize that the grades at the end of the pipeline are not what they wanted to fulfill, right? So that's waste. But if we have these scanners during the transportation and the conveyance stage, we can probably try to minimize that waste at the end, right? We can try to predict what the optical sorter, the more sophisticated sorter, is going to do at the end. So sweet potato packers, they care, when it comes to phenotyping, they care about 6 things. They care about shape and size, they care about weight, flesh and diseases in the flesh, skinning, and rot. But the current optical sophisticated solutions out there, they're only looking at shape, size, and weight. That's how they are sorting things. In fact, they actually compute weight by looking at the shape and size, and then they sort based on weight. So to begin our research, we decided to attempt reproducing shape, size, and weight with more cost-effective scanners. So our first step was training a masked CNN model to extract the morphological features, the simple ones, right? Length, width, or diameter, and area, phenotypes, and we used masked CNN. So masked CNN is, I think most of you guys know what it is. It's a model that delineates the silhouette, which is useful for phenotyping purposes. From here, we can extract those phenotypes, and then we can compute or approximate weight empirically. We found a linear relationship between the area and weight in the logarithmic scale, so we can leverage this kind of empirical modeling to enable 2D phenotyping or 2D scanning during the post-harvest pipeline. So the way they're grading, the grading happens using weight conditions. So the 6 classes are small, medium, large 1, large 2, extra large, and giants. And so the optical sorters, at the end, they do something like this. You see a distribution of how many smalls, how many mediums, how many large, XL, and giant square there. So if we can create or replicate this earlier during the pipeline, we can potentially predict what the optical sorter is going to do. So let's talk about the scanners, the cost-effective scanners, right? The first one is the top-in scanner. This one is placed in the transportation stage, so trucks are going to come in from the field into storage and pass underneath that framework. What this is a portable trailer equipped with a mast that extends up to 5.5 meters, and at the top it has a beam that has the electronics mounted in, right? So it has a flashing system, and the imaging camera is a 60 megapixel RGB Triton camera that takes the images as you see in the top right. Then on the side you have the same camera, but looking at the side of the bins. Here there's a QR code, or you're detecting the QR from the bins and extracting field information. From here you can see, you can get where that bin came from, who harvested that, and so on. We also have a Raspberry Pi camera taking images consistently and computing differences between the images just to detect motion. That's how we're triggering the 2 other cameras such that we can then associate both of these images through a timestamp. Okay. Now, of course, trucks come in different heights, so calibrating our measurements is going to be a big challenge. So I'm going to quickly go through how we're calibrating our measurements. For each image that you have, we remove the background, and then we sum all of the pixels for each column in that background to create a signal that looks like this. And then from that signal, we're essentially taking the derivative of this signal to get the leftmost point and the rightmost point of this bin. At this point, we can then get a calibration factor because we know exactly how these bins are in width, right? And it's standard across all of the United States. So we compute this calibration factor to the area that is extracted from the masked CNN, right, in pixels, but now we have it in inches squared. We compute that into the weight modeling, and that's how we're obtaining our approximated weights in our systems. So now we have a glimpse of, this is after the masked CNN, and we have a glimpse of the size distribution in each truck passing by with calibrated information. This is better than conventional methods, right? Conventional method is someone goes in, they look at the bin, oh, we think it's a medium, it's full medium. So the entire bin is assigned a medium. Here, we're taking a more quantitative approach to grading, and it might not be exactly accurate because you're only looking at the top layer, but the question is it representative of what's underneath? We don't know, we'll have to test that out, right? But the whole goal, again, is to reduce waste by supporting data-driven decision making. The next scanner happens a little bit later, once you're dumping all of the sweet potatoes out into the sorting machines. Between this stage and the sorting step with the more sophisticated scanner, there's about 7 to 10 minutes. And so enough time for them to make a decision if they want to switch fields or not, right? It's also a 60 megapixel RGB camera, and it's connected to a Hall sensor attached to the shaft of the conveyor. Every time there is a revolution of the shaft moving, it sends an electric signal to trigger that camera. So it makes this system speed invariant, so they can run this at many different speeds and it won't matter. We're going to capture every single sweet potato. The difference here with the other system, of course, is that you're imaging every single sweet potato. All the sweet potatoes are in one layer, so this should be more accurate compared to the more sophisticated scan. So we can then, when we pass things through the MassCar CNN, we know exactly what the width of would correspond to one revolution in the shaft. So every single sweet potato is going to pass at least once through this ROI. Right? So here we're obtaining more accurate phenomic data. And when it comes to the calibration, it's as simple as just finding something that you know the actual dimensions of, and we can get the calibration factor like this. And in this case, we used a white clipboard that was 9 inches wide. So in summary, we have two systems. We have a top-in scanner, and we have an eliminator table scanner. Oh, and I forgot to mention, it's called an eliminator table because the sweet potatoes fall through the gaps, the small ones, and then there's also people there eliminating the bad sweet potatoes out, right? So it's called the eliminator table scanner. But they're fully automated. We're getting terabyte levels of data, thousands of images daily. And I guess the whole point here is that the benefit of working with industry is that we can do this and it's hands off after that, right? They do commercial work. It's value for them, but we get to expedite our research process with real commercial problems and real commercial applications. And so we learn from each other, right? They're finding problems in the whole system, and then we tweak, and then we're like, okay, we reformulate our research questions based on what they see. And so it makes things more tangible, right? So just going into a little bit of the results that what we found, the eliminator table compared to the commercial, more sophisticated sorter was very accurate and following very similar distributions. So we can do this, and we were able to replicate those distributions. With the top-in scanner, we didn't get as good of a results, but we're still getting better results than just looking at the bin and visually inspections, right? I did run, some statistical analysis, and there were no statistical differences from the smalls to the extra large, but we do see some systematic bias towards the giants. We think we can still improve this top bin measurements with more improved accurate predictions in the future. But of course, this is an African session, right? And what I just showed you was an application for North Carolina, where there is large-scale phenotyping. Large-scale phenotyping is possible. There's infrastructure to do this. In Africa, you don't have trucks for transporting sweet potatoes. You have sacks, right? And they put the sweet potatoes in the sacks and they sell it to the local market. There are no conveyor systems. There is limited computational power. So how can low-cost scanning solutions be applied in the absence of post-harvest technology? What our group thinks, is that in-field grading is probably the most feasible solution. And while we might not be able to afford the most sophisticated scanners, we can afford a phone. So we conducted some in-field grading with phones using the same masked CNN and weight modeling that I just presented, but applying it to a phone, at a phone app where you just take an image, you go out in the field, and you extract the counts and the yield of that, or the counts and the weight of whatever you want to image. Some of the results that have already been published show that we are getting really good accurate measurements compared to ground truth data. And we're still obviously working with this phone. So what the application looks like is something like this. You have your phone, and you are getting counts, but also in the information, you get the weights as well. Another potential solution, and I know with previous presenters, they talked about drones. High-throughput drone is high-throughput phenotyping using drones is a possible solution, but I think it's would be more appropriate for breeding programs, right? Probably with already established relationships with whatever agencies they have there that they can conduct their experiments. So you can imagine, and this is what I'm showing you now is actual preliminary data and results happening in Africa. You have breeding programs there, and what they do is that they mount every variety into little groups, as you can see here, and then they fly a drone and collect the data. So then for each little mound, each plot is a different variety. So you can, this would be one variety, you can pass it through the masked CNN. You delineate your plots, there's already software out there that you can do this with, and then get yield estimation by variety. So in this case, we were looking at multiple varieties from NC21, and we were doing, we tried to see how good how good our estimates were compared to the ground truth data. And we were getting an R-square value of 0.95 for the weights, and then for the counts, also very good R-squared values, right? And this is all work done with my colleague and Professor Dr. Craig Jenko. He has really good connections with African breeders. But the biggest bottleneck for advancing phenotyping methods in Africa is the lack of edge processing. We don't have the computational power to have these computers out there in the field. So the solution is having it in your phone, but this means discretizing your models, which could reduce accuracy, right? So we need to test these models with reduced accuracy and see if they still have value. One potential solution is transfer learning our training data into new models and seeing how they perform. So in summary, we have built low-cost, high-throughput scanning solutions that can reproduce the morphological features of sweet potatoes, and we have increased the scale of sweet potato research to industry levels. I think there is big potential for breeding programs to implement low-cost, high-throughput scanning, and I especially see a future with cell phone applications and drone applications in sub-Saharan Africa. Thank you so much.
Thank you, Enrique. Any questions for Enrique?
Yeah. Hi, it was a really interesting talk. Well, first a comment. I believe that nowadays with quantization-aware training models, you can get a very good model in your phone. But my question was more about the calibration in the real scenario, because the more interesting part was when you were using your phones to get the measurements and then estimation of the weight of the sweet potatoes.
Yeah.
How are you doing that?
So you saw in the pictures here, we had some PVC pipes, right? We were using the PVC pipes as to calibrate our measurements. So you would need some kind of ground truth data to apply it to your weight model function, yes. But that is very simple to do. Yeah.
Oh, okay, thank you.
Hi, very nice talk. I was just thinking when you mentioned about sacks and Africa, if you had the 2D dimensions, essentially in length and width of your sack, when they fill it, can you use your phone to do a 3D reconstruction and get an estimate on just from the bulge, like in 3D space for what the estimated yield might be?
Yeah, I would imagine you could be able to do that. I've actually never been to Africa and done this. All I know about Africa is that what Dr. Craig Janko has told me, but I would imagine you could apply something like that. I think that's actually a very good, very interesting comment of yours. Thank you so much.
Yeah, do you have any idea about image processing capabilities in sub-Saharan Africa? And does it really make it more feasible than weighing the sack?
So you mean can you repeat that question? Sorry.
Yeah, well, you get the drawing data, right?
Yes. Yeah.
You need to process it.
Yes.
Somewhere.
Yeah.
How do you envision doing that? And if you need to organize all that, maybe it's more feasible than to just weigh the sack instead.
I think for when you have so many plots and varieties, and I think if you have the software to do it real time, and I think it's a potential solution. I think it's something that, of course, you can weigh the sacks, right? And that could be like a ground truth measurement. I think if we wanted to scale things up, we could use the drones. I'm just here presenting some potential solutions or potential applications of high throughput phenotyping that could be applied in Africa. And I think when it comes to Africa, we have to keep things simple first and then actually see value like Jana was saying, right? But yes, obviously you can always just weigh the sacks, and that's probably what they do right now. Yeah.
Thank you very much for the wonderful talk. I see there's one slide that you are talking about several different factors you want to phenotype. Besides of the size, there are diseases and the skin damage.
Yes.
I was wondering, what will be your plan for detecting those type of things? Because I think there will be like before wash and after wash, there will be a big difference, and the scaling up this part will be a big problem.
Yes.
So I wanted to know your thoughts about this part.
So right now we are looking into skinning. Skinning is, I think, it's the next step because it's the easiest one to detect. Once we get into diseases, now we have to get into the multispectral and hyperspectral cameras. We are putting a lot of efforts into skinning right now because from our relationship with commercial packers, grocery stores don't like sweet potatoes that have skinning, right? So if we can identify where the skinning is occurring, but also how much skinning is there actually, that is value for the packers. When it comes to diseases, flesh diseases, right? A big issue right now in sweet potatoes is root knot nematodes, and those nematodes occur. They have little bumps on the flesh, right? So we're looking at applying different techniques with polarizers to detect that difference in lights and reflectance. So the cool thing about it is that our sensors are already in place, and we are conducting those experiments as I'm talking right now, right? And they are running their they're running their processes, but we will get, it's an ongoing process. Yeah.
Great. Thank you very much.
Yeah.
But just for your reference, we have a huge amount of the data sets that has been annotated for this part.
Oh,
So
amazing.
If you wanted to train your model, always welcome to share the data.
Okay, great. Yeah, absolutely. Thank you so much.
So not quick. Yeah, that was an inspiring talk. There were a lot of concepts in there that are, I think, extremely useful. But you call it phenotyping, and so the storage facility in the US, the example, are they integrating your data at this moment? So
We are integrating our data with their commercial applications. Yes.
But how long does it take from crate arrival till optical sorting?
Okay, so between the storage and the optical sorting, a few months.
Oh,
Yeah.
Helps. And then my actual question, because you mentioned it's called phenotyping, is there a breeder involved that is using the data that is collected by the factory?
So yes, so what they do is they will go into storage. So they pack by fields. So they will go into storage and pick a couple bins from that field and throw it into the optical sorter to see to get a sample of that field. And because they actually don't know what is in that field or what that field represents. So they will first pass it through the optical sorter and then get some sort of distribution. With this, you already have that. You don't have to, you skip that process because you're getting with the top-in imaging, you get a sort of representative quantitative distribution, but on the top-in layer. So that's always the thing, yeah.
Yeah, but that's clear. But then maybe there are some batches from some farmers that show some more defects or smaller size distributions. Is that then linked back to the actual variety that shows these symptoms so that the breeder can come up
with the QR code information? We're getting field level data.
I think this is farmer stuff. Like the farmers are producing these potatoes, not the breeders, right?
This is farmers, yes. This is not breeders. This is an actual farming operation. Yeah.
That's my whole point. So to link the post-harvest data that you collect to an actual breeding company to use that information for decisions on which genotypes to continue on. That's I think that's not integrated in your data analysis. Yet, right?
Yeah.
Okay.
Thanks.
We'll stop there. Thank you very much.
Thank you so much.
Thank you.